Alright, so um, that's kind of the next video, I think, because some people watched my last video, but people just didn't comment any suggestions yet. So I'm here to point some key concepts around Android, around Qualcomm, its security, and this related stuff. If you didn't watch it, the last video, I recommend you to do this because the last video explains why I am here and what I'm planning to do with this Qualcomm low-level stuff, and basically the overview around this project. So please consider to watch it. So let's start. I think maybe a top-down approach is more, I think, can be easier and maybe beginner friendly to to explain stuff. And I'm recording this way and not my screen as the last video because there is nothing to show. I think I will draw some stuff right here, but in general there is nothing to show exactly. So let's start, and please ignore because probably sometime someone will enter in this room and you will hear some beeps, and just ignore, please. So let's start with Android. Android is kind of a Linux operating system, and it differs from the major GNU Linux and this kind of stuff because it actually don't use GNU stuff. It actually is kind of stuff made from scratch because it doesn't use X or Wayland for the graphic server. It doesn't use any kind of related stuff to graphics. The way that people interact with the system is kind of different from a usual Linux system, and yeah, that's pretty much it. As it is Linux, as you may know, it uses the kernel, the Linux kernel. So drivers and the abstractions from hardware are made most from the kernel. That's just a common Linux kernel. The main difference between the kernel that you probably use in your desktop and the kernel that runs in your device, your phone, is because for this example, the Qualcomm ones, they will mostly have some proprietary and drivers that are specific to this device. So when you try to build stuff from your kernel and everything that is you need to the phone to work, all this stuff is actually made into the kernel. You can activate, deactivate stuff. You can patch the kernel source code. You can do a lot of stuff that you can actually do in common Linux operational operating system, you know, like a Debian. Anything that you runs in any Linux, you can build the kernel yourself, you can build stuff by yourself, and you can deploy it through the device. One important thing that I almost forgot to say is that the Android kernel is too volatile, which means that when you try to deploy stuff or remove or modify stuff, is really hard to debug or understand, for example, why stuff works or don't works, because you don't have any kind of a black screen with a T2I and stuff, and the debugging kernel messages and everything related. You just don't have this, which makes the Android development and kernel hacking and much more difficult. And that's where I'm stuck. For example, this device, that's the Mi A2 Lite, aka Daisy, and that's my test bed. I'm doing my experiments in this guy, and for some reason I didn't acknowledge, I actually don't know yet, is I tried to build a custom kernel and it just don't works. It appears like I'm just hit my phone screen and it just don't boot. Like, it shows the Android One logo, and after some seconds the screen just go glitched. I don't know how to explain, but it's what happens in this device, which makes my work a lot of harder, as I have explained before. And I don't know if I'm just with bad luck with this guy, but I'm building the kernel with the config that is compatible with this guy. So now, taking one step down from our explanation of our key concepts, we started in Android, now we are in Linux kernel. So right here, stuff starts to begin complicated, as this struggle that I'm having with this device. For some reason, it just don't boot. It's like I'm messing up with something during the kernel build, and I don't know exactly why. I don't know. I think maybe it should be signing stuff, maybe. But I tried to sign the image. I've tried to build the stock image from this device, as it is a Xiaomi device, and Xiaomi releases its kernel source code for devices and stuff related, and this device have the kernel source code available, but just don't works, and I don't know why. And why am I trying to rebuild the kernel, like to add features and modify stuff? That's one important reason. That's because the kernel communicates with hardware, and when it communicates to hardware, this my research object is the Qualcomm stuff, as I've already said in the latest video. And to communicate, I need to modify stuff for this research, as it is a security research. And when I try to do this, I simply cannot. And now, going one step down. What I'm trying to communicate when I'm trying to rebuild the kernel. According to Bjorn Keller, hope I'm spelling his name correctly, he said that I'm messing around with the XPU, the execution protection units, or access protection units. I don't know exactly what's the most correct. But these components of the Qualcomm device, they just make me its function is to prevent people like me to reading and writing in memory. And as you probably should know, reading and writing memory is some important step in most of the security research, and the low-level exploitation, kernel hacking, and all this related stuff. And I can't read and can't write into memory. I can read in one specific case, but I will talk about this later in this video. So I'm messing around, I'm struggling trying to write in memory, and in some cases to read memory. And what's related to this prevention system, this security system that prevents me to doing such actions? First, we have the Android trust zone. Let me draw something that will help to explain this. So in Android, during the boot process, the Qualcomm makes things a lot of security, makes a lot of security to prevent people from doing this stuff in their chipsets and system on chips and related stuff. So we have the following stuff, like we have let me see, SPL, just a second, and good. So we have this figure that is around the Qualcomm secure boot and related process. We are right here. Let me just add one more thing. Hope you can read. But right here is the kernel. The kernel is loaded by some stuff like the A-boot, and trust zone acts as a security measure to prevent this kind of stuff. And the trust zone, aka the Qualcomm Secure Execution Environment, it just is made on top of the ARM trust zone. And as you may already know, but if you don't, I'll explain right now. Most of the Android devices are ARM devices, ARM or ARM64, or I think it's pretty uncommon to see, but there are also x86 Androids, and that's the instructions, that's the the related stuff that comes around with this architecture. And this architecture is made for phones and stuff, and most Qualcomm stuff works with ARM. And the trust zone right here is the exact step that is probably messing us to read and write the memory. And as far as I know, please correct me in the comments if I'm wrong, the execution protection units or access protection units are right here, because this guy, it actually loads kind of other images that is not the kernel, that's not the Android boot and stuff, and it secures it. Let's just take a step. We are right here and we are talking right here. This dude works in what's called the secure world. The Android, specifically the ARM architecture, besides implement the trust zone and implement two worlds, the secure world and the normal world. And what happens right here? The secure world, it exists just to ensure that the normal world just don't have any kind of privileges and stuff like this, like reading and writing memory and doing some hacky stuff. You just can't do anything because of the secure world. And we are aiming to compromise the secure world. As far as Linux kernel that runs in normal world, it's the only Android. It's not the only. I think there are some applications that have some privilege that are similar to the kernel, but the kernel is the main component that communicates with the secure world, because it has the drivers to communicate with trust zone. And I'm trying to in first place to pound the trust zone because of this. The kernel trust zone modules and stuff that communicates, it should use some hardware flaw, some vulnerability, some procedure that may allow me to write in memory or read in memory. And trust zone has this through the ARM architecture, have these two worlds. So if I can compromise the trust zone, I can compromise the entire stack of secure world stuff. And what we have in both worlds, the normal world, we have mostly the operating system like Android and the kernel, the applications and related stuff. But in the secure world, we have also applications, but we have mostly some levels of privilege that is called the exception levels, that goes from 0, that's the most unprivileged, to exception level 3, that's the most privileged. And in exception level 3, we should by default we should be able to do anything, because that's the most privileged level of stuff in ARM architecture. And the trust zone runs in secure world. So we have applications that in secure world should be at exception level 0, and we have also kernel in exception level 1, if I can remember correctly. If we had some hypervisor or stuff like this, it should be at exception level 2, but it's usually not implemented so far. And at the exception level 3, we have the trust zone by itself. and it controls everything, and it allows me to it prevents me to read or write in memory. And if I can power trust zone, I have said, I can do lots of stuffs, at least in the normal world, because the secure world prevents anything in the normal world to compromise secure world and the normal world itself. And Android implements some kind of sandboxing for its apps, so it's kind of hard to an app to access some another app content like memory and even data. Data is separated in some different directories and users. Each app should have in normal Android its own user, and which makes pretty difficult to compromise Android by itself. So in Trust Zone we have this, and some more stuff that Trust Zone do. It also, as I've said before, it loads some images. Like in this figure, the Trust Zone is loaded by SBL or XBL, depends on your device. And I hope you can read all this stuff. But the SBL is loaded by primary bootloader or the boot ROM or stuff like this. You can read more about this in the Aleph Security blog posts. I've said in the latest video that I recommend you to read about this, because they come from here and go like compromise all this stuff from here. Like primary bootloader, it is a read-only memory. You cannot write, you cannot overwrite, you cannot do anything. It just is in your Qualcomm device, and you can't do anything to mess with it or try to modify it. But Qualcomm implements some species of second level of bootloading, which is the secondary bootloader or the emergency download mode that should load a firehose programmer. And this firehose programmer is kind of I don't know how I can call this, but I think it's some species of evolution of a previous protocol called Sahara. And with this more modern way to write in the flash memory, which is where your phone files and images are stored, you should be able to compromise this, to compromise the entire secure boot chain, which implements secure secondary bootloader, which is verified its hash, not only the hash but it's signed, and how this image is verified, its signature. Basically, the Qualcomm devices implement the primary bootloader, but it also implements one important component, that is key fuses. The key fuses, because it's actually unfused. You have a fuse. It's just a wire, and when, for example, in your house, when something goes wrong with the energy, the fuse should open, and that's exactly what key fuses do. But not to save the device from some high voltage, from some high current. the reason that key fuses exist is to hard code in hardware the entire original equipment manufacturer, aka OEM, keys and its certificate chain and public keys and stuff that can be used to verify the integrity and if the images are properly signed. So secondary bootloaders primary bootloader implements this verification of the secondary bootloader image, and the secondary bootloader image implements the same stuff but for trust zone and for the Android bootloader. These two stuff do this exactly same procedure. And talking about trust zone, in this case, that is my current research object. Trust zone loads and verifies the same way some other images. For example, the hexagon images. The hexagon is the most recent Qualcomm's digital signal processor, aka DSP, and TrustZone loads its memory, its image from the eMMC flash chip, and if hexagon isn't properly signed, you just can't load it. And what happens when you try to load an unsigned image? In any case, maybe at kernel, at a boot, Android boot level, maybe at the trust zone level, doesn't matter. Maybe at secondary bootload level, your device just don't boot up. If you try to, write, for example, using the firehose in the emergency download mode, if you try to use this to write an unsigned image, for example, of secondary bootloader, trust zone, your device just don't boot. Your device simply goes through emergency download mode. And the only way to revert this is opening your phone and shorting the communication pins that allows us to physically enter in the emergency download mode. So from this, what we have is a pretty strong and solid chain of trust, as is often called the root of trust. You can just do anything about it, and a lot of devices are interesting to do this kind of research. That is the unfused devices, because the unfused ones don't implement any kind of key fuses, and if it don't implement any kind of key fuses, you can simply load any image you want and you don't need to sign it. And that's, I think, the biggest problem we try to bypass during this kind of research, because everything is signed, everything is verified, and you just the only resource you have to accomplish some kind of exploitation is actually have a hardware exploit or some manufacturer exploit or some exploit that is actually built in the signed images, and that's where I'm stuck at this moment. I can't simply load some kind of image. And back into the hexagon, which this main research object. Hexagon is verified by TrustZone. But there's one more issue with this. If trust zone isn't loaded, it doesn't load any kind of image like the hexagon one, and I can do anything about it. And you may say, oh, but if you are trying to pound the device from the normal world to the secure world, why can't you, for instance, compromise the hexagon from the normal world? And the reason is quite simple, because hexagon doesn't run in secure world. Hexagon is a proprietary architecture that runs isolated over the air from every other stuff. For example, not even trust zone can touch hexagon after it's load, after it's being loaded. When trust zone loads the hexagon image, everything that happens is trust zone loads the modem boot authenticator, MBA, and if everything goes okay, basically trust zone uses some protection units to prevent even itself from communicating with hexagon for stuff like controlling its memory, because hexagon memory it's totally separated from everything. It's almost like a separated device inside your device. Like it runs its own operating system that is a real-time operating system. Back then I think it was called Rex, but now, if I can remember correctly, it's called QOS or QRTOS, something like this. I don't remember at this time, but you can check at the Guillaume Delug. I hope I spelled his name correctly, but the guy that started doing some low-level exploitation, and it used portable, a USB modem, portable Qualcomm modem that you plug into your PC, and when you plug into your PC, you can access the mobile networks. And it studied how this modem works, how it communicates to operating system, and how some daemon like a modem manager, some controller can communicate with it, and it communicates using some kind of special messages like the Qualcomm MSM interface for more modern Qualcomm devices. Back to the Rex operating system, real-time operating system, I don't remember if it already implements this kind of interface, but it communicates to the host device, which is the computer. When you plug the modem into your PC. So all this stuff you simply can't touch. By the way, you must compromise hexagon from the secure world before it's being loaded, because the protection units are implemented in the the hexagon image and stuff, and after implementing these security measures, what happens is that trust zone can't touch in hexagon stuff like processor, instructions, memory, cache. You can't touch anything. It runs literally isolated from everything, isolated from the main application processor. I think that's maybe use it to refer to the main processor that runs in your Qualcomm chipset and stuff. And this far you just can't do some more low-level stuff. As I said, you should compromise it before the image being loaded. And if you can accomplish this, you can do exactly what is shown in the Cartens-Brun's master thesis, which I've mentioned in the last video. And with this, you can, modify the Qualcomm modem image and inject it to your device, and from the device you can do a lot of stuff. For instance, you can communicate directly to the kernel, and you can, for example, intercept some, packages that comes from the mobile networks to your device. You can read the exact header, you can read the exact package bytes, and that's one pretty nice stuff. You have some species of interface that you can use back then. I don't know if if they are relevant today, because, as I've said, Qualcomm implemented some more sophisticated interfaces like the Qualcomm MSM interface. But back then you have the DIAG, that is a diagnostic interface, and you have some nice projects like the Mobile Insight, you have the Snoop Snitch, you have the QC Super, which uses the DIAG interface. Your device must be rooted in order to use this interface, but it gives you some low-level primitive powers, because you can read stuff, but you can't communicate to the device by default. Like, I don't know, I want to, maybe send some package, some arbitrary package to the interface, and it sends this package to the mobile, for example, the mobile basement, which is implemented at the Hexagon. Hexagon actually implements some stuff that is more than just an architecture, is more than just a digital signal processor. It's a cluster of digital signal processors, like for audio, for video, for modem. It has the mobile networks. You have, I think, compute, that's probably some stuff related to neural networks, and you have a lot of this stuff, and you can touch it. It actually manages it by itself, and it's kinda hard to access it. And the DIAG interface actually can communicate in order to give some diagnostic information around the Hexagon. You also have the old AT commands. AT, I don't know what it stands for, but are commands that most devices, modems, and related stuff implement in order to communicate in a primitive way to the device. For instance, if you have a Bluetooth module that you, for instance, you want to do some Arduino project that uses Bluetooth, you can use this Bluetooth module, and you can configure, for instance, its password, its I think MAC address, I'm not sure. You can control which devices it should allow, if it should connect to a device, all this stuff you do by using AT commands. Not only this, but your Wi-Fi stuff probably uses some AT commands back then. As I've said, nowadays the companies, the OEMs, are implementing their own proprietary communication stuff. So it's hard to explain, but some stuff are already implemented in order to achieve some backward compatibility, and people are nowadays still trying to compromise Qualcomm stuff via AT commands, via DIAG, and this related stuff. And AT commands is I don't know, probably a nice approach to invest some time, but as I said, it's a legacy interface, and probably you should not you probably not be able to communicate and do some low level stuff right here with AT commands, but it's two interfaces that you have. I think GPS actually also uses the AT commands. As I said, most of the stuff, basebands and modem and Bluetooth and Wi-Fi and all this stuff. Okay, this I think this PC just. Oh, alright. Most of this stuff actually implements some kind of interface to communicate with, and with Qualcomm we have now QMI, that is Qualcomm MSM interface, and that's my main goal. I think I can call like this, but in order to accomplish this, I must be able to communicate with Hexagon, and I can't spawn any kind of QMI commands and communication and stuff without prior compromise of the stock image, and that's very sad. I mean, I can actually buy some devices that should be cheaper and should be also unfused, so I will not have any kind of this trouble trying to pound stuff and trust zone, Hexagon, and the entire secure boot chain that Qualcomm implements. But I really want to compromise my device. It was released, I think, in July, 2018 July, something like this, with the BA2, aka Jasmine, and yeah, that's a legacy device. So I think I should be able to compromise it, but I don't know. I don't know for a while how to accomplish this, because all my attempts right now, I've followed the Aleph Securities blog posts trying to pound primary bootloader using the emergency download mode. And with the emergency download mode, you should be able to do what? You can emulate this entire boot chain, and emulating this, you should be able to using controlled memory addresses with which you have write and execution permission. You should be able to, for example, run a second primary bootloader that doesn't verify the secondary bootloader, and with this emulated primary bootloader you load the emulated secondary bootloader, and you patched it, and you patch it to don't in order to it doesn't check the trust zone and the Android boot images. When you do this, you also can patch the trust zone because trust zone actually implements some secure boot, security measures. And if you can pawn this, you can basically load any image. In my case, the hexagon image, and with this I can continue with my project. If this can't be accomplished in this device, maybe an attack running from the normal ARM world and trying to go to the secure ARM world. And if I can do this during the boot process, I should be able to compromise stuff. And I think I explained everything. If I wasn't clear, please post it down here in comments below, because I need some help. If you guys have some experience with Qualcomm exploitation and stuff, please send in the comments. It will be really, really helpful, and you probably will appear in the next video. And yeah, if you have some suggestions, if you have any feedback, if you can understand what I'm saying, because I don't know if my accent and speech is being clear enough, but please tell in the comments. And that's it. If I mistake some concept or something, also please post in the comments below, because I'm just a noob trying to pound Qualcomm, Hexagon and Trust Zone. About this, don't forget also to check the comments and description, because I've created a Telegram channel and chat group, where I will post my progress with this, my current status, and also you can interact with me, you can interact with people, you can make friends, you can run some questions, you can maybe share your work around this and maybe around other stuff, because when I finish this, probably I will use this to publish some of my low-level studies, malware development knowledge and stuff, right? And maybe other devices if this goes okay and I can finish this project. So that's it, and hope you liked it. And again, please put your feedback in the comments below or in the Telegram channel. Right? That's it, and see you in the next video, which I have no idea what I can do. So also please put any suggestions in the comments below. Right? That's it, and see you in the next one.